Let us consider an RLC circuit where our voltage potential on the right hand side of t is equal to 0 is equal to 12 volts, and our current initially running through our inductor on the right hand side of t is equal to 0 is equal to 30 milliamps. Given a capacitance of 0.2 microfarads, an inductance of 50 millihenries, and a resistance of 200 ohms, we want to determine the initial current value in each branch, that is IR, IL, and I sub c at t is equal to 0, and our voltage as a function of time. Looking immediately after t is equal to 0, the current in the inductor is equal to our given initial current for all t is greater than 0, such that I of L when t is equal to 0 is equal to 30 milliamps, i.e. the current initially running through our inductor. We note that the voltage potential across all elements is 12 volts. Thus, the current found through the resistor is simply done via Ohm's law. I sub R when time t is equal to 0 is equal to our voltage potential per our resistance. That is, we'd have 12 volts per 200 ohms, or 60 milliamps would be running through our resistor. Lastly, applying KCL at our top node, our current running through our capacitor is a negative of I sub R plus I sub L, or we'd have minus 90 milliamps running through our capacitor, i.e. our capacitor is discharging. Now, to determine the behavior of our voltage as a function of time, we need to look at the roots of our equation, i.e. we need to populate lambda 1 and lambda 2 such that we can solve our second order ordinary linear differential equation. To do such, alpha is equal to 1 per 2 RC, where we'd have 1 per 2 times our resistance, 200 ohms, times our capacitance, 0.2 microfarads, or alpha is equal to 12,500 seconds to minus 1. Omega naught is 1 per the square root of LC, or 1 per the square root of 50 millihenries, times 0.2 microfarads, or we'd have 10,000 seconds to minus 1. That is, lambda 1 would be equal to minus 5,000 seconds to minus 1, and lambda 2 would be equal to minus 20,000 seconds to minus 1. Thus, our solution takes the form v of t is equal to a1 e to lambda 1t plus a2 e to lambda 2t. Or we'd have a1 e to minus 5,000t plus a2 e to minus 20,000t. To determine the constants a1 and a2, we need to apply our initial condition, as well as the time rate of change of voltage. At time t is equal to 0, the voltage across our system is 12 volts, or a1 plus a2 is equal to 12 volts. We also know that the current running through the capacitor, I sub c, is expressed as our capacitance times the time rate of change of our voltage, or the time rate of change of our voltage is equal to I sub c per c, where I sub c was found to be minus 90 milliamps and our capacitance was found to be 0.2 microfarads, or we'd have a value of minus 450,000 volts per second. Now, to differentiate our solution such that we can apply the dV/dt we just found, that is, we'll take the time rate of change of a1 e to lambda 1t plus a2 e to lambda 2t, and evaluate this when time is equal to 0. Thus, if we take the derivative of our voltage with respect to time when time is equal to 0, we'd have minus 5,000 a1 minus 20,000 a2 would be equal to minus 450,000. Thus, we have two equations and two unknowns, and we can solve for our coefficients. a1 is equal to minus 14 volts, and a2 is equal to 26 volts. Thus, the final form of our solution is our voltage as a function of time is equal to minus 14 e to minus 5,000t plus 26 e to the minus 20,000t. If we graph our solution, we see that we start at 12 volts, and we go down to about negative 5 volts within a period of about 0.1 milliseconds. And then our voltage potential begins to asymptotically approach 0. This type of solution is known as an overdamped response, where we overshoot our steady state solution, i.e. 0 volts. An overdamped response is quantified when alpha squared is greater than omega naught squared.